In this lesson, we're going to cover two-step dimensional analysis problems. Our first example asks us how many hours there are in 16.2 years. So we're converting from years to hours. If you know off the top of your head how many hours there are in a year, you can do this conversion in one step. I am not one of those people, so I will convert 16.2 years first to days and then to hours. So my conversion factors are 1 year equals 365 days and 1 day equals 24 hours. I'm going to begin this problem by writing the given value, 16.2 years. Our first step is to eliminate the years label. So to do that, we need to write the unit years in the denominator position of our conversion factor. And then since we're given 1 year equals 365 days, days will be in the numerator portion of this conversion factor. We're going to plug in our numbers. 1 year equals 365 days. And I do that so that the years cancel, and then we'll be able to multiply the numbers up at the top, which are the numerators. If we solved at this point, our answer would be in days. But since we're asked for hours, we have to go one more step. And to get rid of days, we're going to put days in the denominator. So days in the denominator. And we're given 1 day equals 24 hours. And those are the units that we want our answer. We want hours in our final answer. So we'll put hours at the top. In 1 day, there are 24 hours. And we're going to cancel the unit days. And now we're going to solve. So remember, when you are performing a calculation using dimensional analysis, the top row, those are all numerators, and we get to multiply across. So 16.2 times 365 times 24. That gives us 141,912 hours. Now, when we're recording our answer, we're only going to be recording significant digits. So look at our given value, 16.2. That's 3 significant digits. So that means we get to round our calculator answer to 142,000 hours. Now, if the question asks us to write our final answer in scientific notation, we would need to move the decimal 1, 2, 3, 4, 5 places to the left. Remember, when we go to the left with a decimal point, our exponent becomes positive. So 1.42 times 10 to the power of 5 hours would be our answer in scientific notation. Number 2 asks, how many milliliters are in a 5.00 gallon bucket? So we're going from an English to metric conversion here. Remember, English to metric, those conversions factors you don't need to know. You're not responsible for those. You're only responsible for conversions within the metric system. So for this problem, we're given 1 liter equals 1,000 milliliters, and 1 gallon equals 3.785 liters. So if we're planning out our setup, we would go from gallons, since that's our given value, to liters first, and then from liters to milliliters. So those are going to be our steps. Let's begin by writing our given value. So 5.00 gallons. And then our next step is to get rid of gallons. So we're going to write gallons in the denominator of our conversion factor and change gallons to liters. So we'll copy the values exactly as they're written. 1 gallon equals 3.785 liters. Notice how the gallons cancel. Our next step, now that we've converted to liters, is to change to milliliters. So liters will go in the denominator, milliliters up at the top, and we'll again, just copy the numbers in from our conversion factor list. 1 liter equals 1,000 milliliters. Cancel out your liters, and all we're doing now is multiplying all the numbers at the top, or all the numbers in the numerator. So 5.00 times 3.785 times 1,000. And that gives us a calculator answer of 18,925. If you look at our given value, 5.00, that's 3 significant digits. So our final answer then will be rounded to also 3 significant digits, 18,900 milliliters. Now, if the instructions say to record this answer in scientific notation, you would then move the decimal point 1, 2, 3, 4 places to the left. And remember, when you're moving to the left, you're going to add to your exponent. So 1.89 times 10 to the power of 4 milliliters is our answer. Number 3, there are 95 milligrams of caffeine in a cup of coffee. How much or how many kilograms of caffeine is this? This problem has units that are within the metric system. So if you know the conversion factor to get from milligrams to kilograms, you can do this in one step. But that's not information that you're required to retain. What you should be able to do, though, is to convert from milligrams to grams, the base unit, to kilograms. Let's bring in our table of prefixes to see where everything is. So we're starting with milligrams. Okay, 95 milligrams is what we're given. So the way we interpret this table of prefixes is 1 milligram equals 1 times 10 to the negative 3 grams. Or you could say 1 milligram equals 0.001 grams. And then the other prefix that is in this problem is the kilogram or kilo. So the way to interpret that is 1 kilogram equals 1 times 10 to the power of 3 grams, or 1,000 grams. There's our conversion factors. So we're going to begin by writing the given value down, 95 milligrams. Now to cancel out milligrams, we need to put milligrams in the denominator position. And we're converting to, remember, the base unit, which is grams. That'll go up at the top. And just for consistency's sake, when we're using prefixes within the metric system, I'll always assign the prefix the 1. So 1 milligram equals 1 times 10 to the power of negative 3. Okay, and remember, I got that number here, from here. Okay, milligrams cancel. We want to get rid of grams now because we're trying to convert to kilograms. And once again, the prefix gets the 1, so 1 kilogram equals 1 times 10 to the power of positive 3 grams. Remember what you do with exponents, numbers with exponents, when you're dividing. You're supposed to subtract them. So negative 3 minus 3 equals negative 6. So that tells us the exponent our final answer should have. Okay, so let's see how we're going to fit that in. Our answer will come out to 95 times 10 to the power of negative 6. Now here's the thing. If you're going to write this in scientific notation, you're going to need to move the decimal point 1 place to the left so it's in the right position, so that there's only one non-zero integer in front of the decimal. When you move the decimal point 1 place to the left, you're going to add 1 to the exponent. So our final answer in scientific notation will come out to 9.5 times 10 to the power of negative 5. And don't forget your units. Remember, the grams cancel, and we end up with kilograms. Let's verify our calculation here using a calculator. 95 times 1, find that exponent button, negative 3 equals, divided by 1 exponent 3 equals. Our calculator answer comes out to 0.000095. When you change the scientific notation, you're going to move the decimal point over 1, 2, 3, 4, 5 places to the right. And remember, when you move the decimal point to the right, you end up with a negative exponent. Number 4, the volume of an average balloon is 0.141 hectoliters. How many deciliters is this? So once again, conversion within the metric system, prefixes that should be familiar to you. So you will not be given conversion factors for this type of problem. Okay, let's begin by looking at our pathway. So we're going to go from hectoliters to our base unit liters, and then finally to deciliters. Let's bring in our prefix table and find hectoliter. So hectoliter is right here, and the way to interpret this is 1 hectoliter equals 1 times 10 to the power of 2 liters, or 100 liters. And then let's look for deciliter. It's right over here. And the way to interpret this is 1 deciliter equals 1 times 10 to the power of negative 1 liters, or 0.1 liters. So now that we have our prefixes sorted out, these are our conversion factors. And we're going to begin by writing in our given value, 0.141 hectoliters, and set up our dimensional analysis table. So we want to get rid of hectoliters, so to cancel that out, that goes in the denominator of our conversion factor. And then up at the top, we're going to convert to liters. And now you simply plug in your numbers. So we're going to stick with prefix gets the 1. So 1 hectoliter equals 1 times 10 to the power of 2 liters. Cancel out hectoliters, and we can move on to convert liters to deciliters. So liters are at the bottom, so we can cancel them. And it's 1 deciliter equals 1 times 10 to the power of negative 1 liters. When you have exponents on numbers that you're dividing, remember to subtract. So 2 minus negative 1, okay? Minus becomes plus, right? So 2 plus 1 is 3. So our exponent will be 3. So let's go ahead and write 0.141 times 10 to the power of 3. Now, this is not scientific notation. In order to write our answer in scientific notation, we're going to move the decimal point over one place to the right. When we do that, we're going to subtract 1 from our exponent. So our final answer comes out to 1.41 times 10 to the power of 2. And don't forget your units. Remember, the liters cancel, so we end up with deciliters in our answer. Let's use our calculator to verify. 0.141 times 1 exponent 2 equals, divided by 1 exponent 1 negative equals. So that's 141. If we write 141 and change that to scientific notation by moving the decimal point over 2 places to the left, we get a positive 2 exponent. Number 5 is a mole conversion. How many moles of Fe, which is iron, is equivalent to 8.725 times 10 to the power of 28 atoms of iron? So our conversion factor is going to be 1 mole equals 6.02 times 10 to the power of 23 atoms. This is a one-step problem, so we're just going to get rid of that there. 8.725 times 10 to the power of 28 atoms, Fe. We're going to get rid of atoms of Fe, so we're going to put that number, or put that label rather, at the bottom, atoms of Fe, and we're changing this to moles of Fe. So we're going to put moles of Fe at the top. Look at your conversion factor. It's 1 mole. 1 mole of Fe equals 6.02 times 10 to the power of 23 atoms. Okay, remember, when you are dividing numbers with exponents, you're going to subtract them. So 28 minus 23 is going to be about 5. Okay, so your exponent should be around 5. If it's a little higher or a little lower, that's probably okay. But if your exponent comes out to 51, that means your calculator added instead of subtracted the exponents, and there's something wrong with your calculation, so you might have to do it again. I'm just showing you this step where you can kind of predict what your exponent will be to help you check your work as you move through these problems. Okay, so let's solve. 8.725 exponent 28 divided by 6.02 exponent 23. Okay, so our calculator answer comes out to 144,933. So we actually only need 4 digits that are significant in our final answer. So we're actually going to change these to zeros, placeholder zeros. And to write our answer in scientific notation, we'll need to move the decimal point over 1, 2, 3, 4, 5 places to the left. And remember, when we go left, we're going to add to our exponent. So 1.449, 4 significant digits, times 10 to the power of 5. Okay, and since we canceled out atoms, our final answer is in moles of iron. Our final problem, number 6, is a problem for honors chemistry students. A certain walkie-talkie has a communication range of up to 5.718 times 10 to the power of 13 nanometers. What is the range in kilometers? So for our purposes in solving this problem, we're going to go from nanometers to the base unit, which is meters, to kilometers. Let's take a look at our table of prefixes. So we're starting with nanometers, which is over here. So you could say 1 nanometer equals 1 times 10 to the power of -9 meters. And then our other prefix that we're working with is kilometers. So 1 kilometer equals 1,000 meters, or you could say 1 times 10 to the power of 3 meters. Okay, so now that we have our conversion factors, we can get started. 5.718 times 10 to the power of 13 nanometers. We're going to cancel out nanometers, so nanometers will go in the denominator. And we're changing this to the base unit, which is meters. So I'm going to stick with my prefix gets the 1 and put our equivalent value in meters up at the top. 1 times 10 to the -9. Okay, we got rid of nanometers. Now we need to get rid of meters to convert to kilometers. So meters at the bottom, kilometers at the top. 1 kilometer in the numerator equals 1 times 10 to the power of 3 meters. Okay, we have a few exponents here this time. So let's take a look at how we can predict what our exponent will be. So we have 13 and -9 in the numerator. When you have numbers with exponents that you're multiplying, you're going to actually add the exponent. So 13 plus -9, that's going to equal to +4. And then look at your other exponent in the denominator, the 3. So because it's in the denominator, you're going to subtract. So 4 minus 3 equals 1. So our exponent will just be 1. Okay, let's solve. When you multiply across, because there's 5.718 in our given value and the rest of the values are just ones, we can simply write 5.718 times 10 to the power of 1. And then look at your labels. Meters cancel, so we end up with kilometers. Okay, let's do this on the calculator to verify. So 5.718 exponent 13 times 1 exponent 9, don't forget the negative sign, equals. Okay, divided by 1 exponent 3 equals. Okay, so our calculator answer comes out to 57.18. And remember, if you move the decimal over to write this in scientific notation, one place to the left, that means you're going to have to add 1 to your exponent, which is what we did here. So that's our final answer. And that's it for two-step dimensional analysis problems.